Hey everyone, and welcome to a brand new explainer. Today, we're stepping virtually into Dr. Kem's laboratory for an absolute masterclass on what has to be one of the most heavily relied upon analytical tools in all of modern science, the UV-Visible Spectrophotometer. Have you ever wondered exactly how scientists can just look at a completely clear liquid and tell you precisely what invisible chemicals are hiding inside it and in what exact concentrations? Well, we're going to find out. We're going to take a really fascinating journey today, literally following a single photon of light from the second it's created, all the way through the intricate inner workings of this incredible instrument. Here is the roadmap for today's masterclass. We'll welcome you to the instrument, look at sources and monochromators, talk about holding the sample, dive into detectors and readout systems, and finally compare single versus double beam setups. All right, Section 1. Welcome to the instrument and the journey of our photon. So, the overarching problem in analytical chemistry is identifying and quantifying stuff we simply cannot see with the naked eye. UV-Visible Spectroscopy solves this by exploiting one really simple, beautiful principle. Different molecules observe specific, highly precise wavelengths of light based on their unique electronic makeup. To measure this, we follow a roadmap of 5 sequential components. We start at the source, move over to the wavelength selector, which we call a monochromator, pass right through the sample cell, hit the detector, and finally translate all of that into data at the readout system. Pretty much every single UV-Vis spectrophotometer in the world relies on this fundamental 5-step anatomy to track exactly what light goes in and exactly what light goes missing. Moving right along to Section 2, Sources and Monochromators, Creating and Filtering Our Light. The journey of our photon obviously has to begin with its creation. But, we can't just screw in a standard light bulb here. We need to generate a broad, super stable spectrum of light first, before we can isolate the exact energy we need. And to cover the full range, these instruments typically use 2 totally distinct lamps. For the ultraviolet region, that's from 190 to 380 nanometers, we use a deuterium arc lamp. It's a gas discharge lamp that gives us this beautifully continuous UV spectrum. But for the visible and near-infrared regions, stretching from 350 all the way out to 2500 nanometers, the instrument actually switches over to a tungsten halogen lamp. This one operates at an intense 3000 Kelvin to give us highly stable visible light. Okay, so once we have all that light, we immediately face a problem. We absolutely cannot use it all at once. If we blasted our sample with the entire spectrum, our data would just be a chaotic mess. So the monochromator steps in to act as a highly specific filter. It takes that broad beam of light, disperses it out into its individual wavelengths, and then uses a super narrow exit slit to isolate just the exact wavelength, the exact color or UV frequency that we need to interact with the specific chemical we're analyzing. But how does it actually separate the light? Well, historically, older instruments used prisms, but as our notes from Dr. Kem point out, prisms have a non-linear dispersion. That essentially means they spread UV light out way more than visible light, and they also suffer from lower efficiency because of reflection losses. Modern instruments instead use what are called diffraction gratings. Gratings are amazing because they provide a linear, totally uniform dispersion across the entire range, and they are highly efficient. They're absolutely the gold standard for getting our single photon perfectly isolated. Section 3. Holding the sample, the crucial cuvette. Our photon now leaves the monochromator and enters the sample compartment. This is where it will actually interact with the chemical inside a little rectangular sample holder known as a cuvette. Now, if you're just doing visible light spectroscopy, a cheap optical glass or even a plastic cuvette is perfectly fine. But here's the catch. Standard optical glass strongly absorbs ultraviolet light below 320 nanometers. Literally, if you put your UV sample in regular glass, the glass itself absorbs the photon, and your detector sees absolutely nothing. Because of this, for UV studies, you have to use specialized, highly transparent cuvettes made from fused silica or quartz. And because these expensive quartz cuvettes are the critical window for a photon, Dr. Kem has some incredibly strict lab rules for them. You have to keep these surfaces scrupulously clean. A single fingerprint contains oils that will block or scatter your UV light, completely ruining your data. No way around it. You wash them only with distilled water, dilute alcohol, or acetone. And most importantly, you'll notice that cuvettes have clear optical sides for the light to pass through and frosted sides for your fingers. You must always, always handle them by the frosted sides. All right, Section 4, Detectors and Readout Systems. Catching the signal. So our photon has survived the journey. It was created, it was filtered, and it successfully passed right through the quartz cuvette without being absorbed by the sample. But now, that physical light has to be caught and translated. This brings us to the detector. Simply put, it acts as a translator between the physical realm of light energy and the digital realm of electrical data. It takes those incoming photons and converts them into an electrical current that a readout system can actually plot onto a graph for us. For really highly sensitive scanning instruments, the ultimate detector is the photomultiplier tube, or PMT. This is an incredibly sensitive vacuum tube designed specifically for situations where a sample is highly concentrated and very, very little light actually makes it through. A PMT is so incredibly sensitive, it can literally detect single photons. But how exactly does it turn one tiny microscopic photon into a readable computer signal? It does it using this really ingenious cascading effect. Let's break it down. Step 1. Our lone incoming photon strikes a primary photocathode, knocking loose just a single electron. Step 2. That one electron is accelerated by a magnetic field toward a curved metal plate called a dynode. Inside the tube, there are 8 to 10 of these dynodes, and each one has a higher electrical potential than the last. We're talking a jump of 75 to 100 volts per step. So when our one electron hits the first dynode, it knocks loose several secondary electrons. Those hit the next dynode, knocking loose dozens, then hundreds, then thousands. By step 3, this visceral, literal electron avalanche reaches the final anode collector, multiplying that original single photon by a factor of up to 100 million into a massive, easily readable electrical signal. It's amazing. Finally, Section 5, Single versus Double Beam, Solving the Drift Problem. Okay, we have all the pieces of our instrument, but we still need to address a pretty fatal flaw in the basic design. What happens if the light source flickers, or its intensity naturally fades over time while you're running a long experiment? This brings us to the crucial difference between single beam and double beam spectrophotometers. In a simpler single beam instrument, there's only one optical path. You have to put a blank solvent in the machine, measure its baseline, take the cuvette out, put your real sample in, and measure that. The fatal flaw here is time. If the intensity of your lamp drifts or fluctuates between the time you measure the blank and the time you measure the sample, your data is totally inaccurate. A double beam instrument solves this so elegantly. It uses a beam splitter to divide the light into 2 paths. It actually measures your sample and your blank simultaneously, creating automatic drift compensation. The crucial difference is really found in the math. In a single beam transmittance calculation, you are dividing the sample measurement by a blank that you recorded in the past. If the lamp changed, those 2 numbers are out of sync. But in the double beam formula, the instrument continuously records the ratio of the sample beam intensity over the reference beam intensity at the exact same fraction of a second. Because any fluctuation or flicker in the lamp's brightness happens to both beams equally, the ratio stays mathematically perfect. The error completely cancels itself out. Let's look at how this builds into real-world data, because this graph is really the big aha moment of our masterclass. We're tracking measurement stability over 3,600 seconds. The blue line here is the single beam instrument. You can clearly see it drifting downwards into negative absorbance as the lamp naturally fluctuates over time. It's terrible time stability. Now look at the red line. That's the double beam instrument. By constantly referencing the blanks simultaneously, the optical design ingeniously neutralizes that source drift to provide a perfectly stable, flatline output. Just brilliant engineering. Which brings us to the end of our journey with the photon. From the intense glow of a deuterium lamp, perfectly filtered by a diffraction grating, safely passed through a pristine quartz cuvette, amplified by a millionfold inside a photomultiplier tube, and perfectly stabilized by double beam optics, we've really seen how brilliant engineering reveals the invisible chemical world. I'll leave you with this thought. How might you apply this brilliant concept of simultaneous referencing, of checking a control at the exact same time as your variable to eliminate unwanted noise and errors in your own future scientific endeavors? Thank you so much for exploring the laboratory with us today in this explainer. Keep questioning, keep analyzing, and keep learning. Catch you next time.